All right, everyone, we're going to get started. So my name is Alyssa Cherbu, and on behalf of Enersource, Hydro One Brampton, and Partners in Project Green, I would like to welcome you to today's webinar. Before we start, I would like to run through a few logistics for the webinar. Note that your lines have been muted, so please type your questions in the chat section as we go, and they will be answered at the very end of the presentations. If you come across any issues throughout the webinar, please send a direct message to myself, TRCA host, within the chat section. So let's begin. So first up, we have Jennifer Taves, Project Manager for Communications and Engagement with Partners in Project Green, to introduce the webinar. Over to you, Jen.
Thanks, Alyssa. And thank you, everyone, for joining the webinar today. We've got a good lineup for you, and I think you'll learn a lot about compressed air systems and how you can uncover some hidden opportunities in them. But just before we start, I'd like to give you a brief introduction to Partners in Project Green, as well as to Enersource and Hydro One Brampton, and how we all can help you in your sustainability journeys. So Partners in Project Green, or a Pearson Eco Business Zone, as many of you know, is this oddly shaped geographic region surrounding Toronto Pearson. We cover the majority of Mississauga, a good chunk of Brampton, and a little bit of Toronto. And what we really aim to do is drive sustainability in our member organizations. We work hard to provide programs and services that assist you in your sustainability journeys, and we have many different resources that are available to you. We have a number of different ways in which we achieve our goals. Most of them are in peer-to-peer learning sessions, just like this one, where you can learn how to build the capacity of your organization to take on sustainability champions. And we also work very heavily in the business-to-business collaboration space, so really finding ways to uncover new business opportunities for businesses to drive sustainability forward in ways that make sense for their bottom line. So you can find more about us at www.partnersinprojectgreen.com. Okay, great. So I just want to talk a little bit about our two local distribution partners who are partnering in today's webinar. So Enersource is a diversified electricity distribution and energy services company focusing on quality of service through innovation and operational excellence, delivery of conservation programs, and smart metering solutions. Hydro One Brampton is responsible for the safe and reliable delivery of electricity to more than 130,000 homes and businesses in the city of Brampton. And you can see their websites up on the screen there. And I encourage you to really take a look at their programming, whether or not you're in Enersource jurisdiction or if you're in the Hydro One Brampton area. Log on and check out what they have available to you. They have many different programs and services that help you reduce your energy costs. So through these webinars, we really do hope to bring you the latest technologies, programs, and tools to the comfort of your office while providing a format to ask questions that will help you deliver the right solutions for your operations. Enersource, Hydro One Brampton, and Partners in Project Green offer many resources to help companies along their journey to sustainability. And I encourage you to visit our websites or get in touch with us after the webinar to learn more about our programs, trainings, and events. This afternoon, we are exploring the topic of compressed air systems and how, by implementing better management practices, your businesses can realize real savings opportunities. We are fortunate to have our speaker, Duff, here from Compressor Science Inc. Chris has over 15 years of auditing experience. He works with Compressor Science Inc., which is a progressive company involved in the auditing, design, and re-engineering of compressed air systems. His focus is on providing solutions to users of compressed air to reduce their energy consumption, improve air quality, and, where possible, provide cost-effective alternatives. Please welcome Chris.
Good afternoon, everybody, and thank you for joining the webinar. Can everybody hear me okay? Okay, I'm just going to run through the presentation here. As soon as I get controls from Melissa. Okay, starting with compressor management, module 1. We're going to talk about different types of compressed air audits, kind of what we do as a company auditing compressed air systems.
Oh, sorry, Chris. I am giving you the mouse right now.
Okay.
And how is that? Did that work?
Yep.
Okay, perfect.
I have controls. Okay. So I just want to go through why do an air audit. A lot of people may have had audits done already or different types of compressed air audits. There's been a lot of types of audits done over the last 20 years through Ontario Hydro and through the new OPA programs that have come out in the last several years. Obviously, we look at doing an audit because most compressed air systems that we deal with have grown and evolved in their business. They've added compressors, they've added machinery, etc. Most companies that we deal with have very little idea of actually how much of their utility bill or what percentage of their bill is represented by compressed air. Doing an audit, a compressed air audit, will give you an idea of what the current operating cost is of the compressed air system and what component of your utility bill that you're paying every month is relegated to compressed air. By understanding where you are as far as what your current costs are and current system setup, you can then plan a course of action for system optimization and control. Implementing these compressed air management initiatives can result in thousands of years in cost reductions. So what we're looking at is long-term sustainability in compressed air energy costs. We're obviously looking for real savings that could be materialized now with a lot of the grants available through OPA and the federal government. We look at the compressed air system as one complete entity. Everything's related in the compressed air system, from the intake of the compressor, how you're pulling air into the building, into the plant, to the compressor, to basically how you're using compressed air at the point of use. The distribution system of compressed air, the dryers, the filtration, everything is related in the compressed air and how it correlates to the energy consumption back at the compressor. So you really, if you're auditing a system, we don't just go in and look at the energy consumption of the machines. We have to look at how they correlate within the system, the compressed air system, because everything is interrelated to how much power is drawn back at the compressor. So if you're not auditing the entire plant, it's pretty difficult to just look and say, okay, well, we're drawing this much energy. This is what we can do by putting a VFD in or changing something in the compressor room. Because really what goes on out in the plant is what dictates what happens back in the compressor room. So by focusing on the total compressor system, we offer basically an unbiased approach to looking at the whole system optimization. Not every audit that we do results in the sale of a new compressor. Sometimes we're looking at changing piping, adding storage, adding controls to existing compressed air systems, whatever is going to help optimize that system and reduce the power consumption at the machine is what we're after. Again, there has to be a payback. You know, a lot of people through the ERE program have put in variable speed drive compressors, have seen some savings, but if you're not resolving the issues that are out in the facility that are causing that compressor to stay loaded or to load unnecessarily, then there isn't going to be sustainable paybacks. So really the purpose of the audit should be looking for opportunities to reduce the total system operating cost, not to just look at buying new equipment, getting some rebate money and moving forward. We've gone into systems where there was, rebates and there was machines put in, and we find out that the VFD is now running flat out because the items out in the plant weren't resolved to begin with. So if there's no sustainable savings, there should be no project. Looking at effective auditing, the person who's auditing your facility should have a good fundamental understanding of most types of compressors, because if you're going in to audit a facility, there's different control schemes, there's modulation, there's load-unload, variable displacement, reciprocating, how those compressors integrate together and integrate with the dryers and the filtration and the piping, and how the demand side of the plant works. Can you get away with using a blower versus compressed air? Should we put nozzles in? Can we switch to electric agitators versus compressed air? These are things that an auditor should have an innate understanding of, who's been auditing compressed air systems, to look at the long-term benefits to the client. other than just changing compressors. Again, on-site presence means that if you're in auditing a compressed air system, you should be present looking at the compressed air system from intake to point of use, how they're using compressed air. A lot of companies come in and they put in the black box study, they hook the amp meters to the compressors, they put a pressure transmitter in, and they come back a week later and download the data without really any correlation to what's going on in the facility, how that's impacting the compressed air system demand. A lot of the LDCs now are getting more fervent on tying production in with the study results because we've done a lot of studies where clients have variable demands throughout the year. They're busy in the summer, they're not as busy in the winter. So in order to get a pretty good baseline for the year, you have to have an understanding of how their production correlates to the electrical demands if there's going to be any sustainable savings. So again, during the collection periods, you want to be looking at how they're using compressed air, taking a look at the size of the compressed air headers, look at the size of the drying and filtration equipment, how they're using compressed air at the point of use. Everything is relative in the compressed air during the audit. So an idea of what to expect in an audit, and again, a lot of people are doing this, some people aren't. This is just sort of what we like to see as far as getting an audit done for a customer where there's actually a full-blown study going on for a week or 2 weeks. Compressed air system leak detection, ultrasonic inspection of the complete piping system, tagging of leaks, pressure differential data logging of the distribution system. That means putting transducers in the compressor room across air treatment equipment out at specific points in the piping to see are there any restrictions out there that are causing the compressed air system to run at a higher than necessary pressure. Data logging, of course, of the compressors for load performance, and power factor measurement at each machine. Power factor measurement is critical because you really need to know what power factor, if you're taking amperage measurements and voltage measurements, how to correlate correctly into kilowatt consumption. Flow measurement of compressed air headers, I think, is critical, especially with upper range modulation compressors and different compressor control schemes. If you're simply taking an amp and a pressure reading and trying to correlate that into a flow measurement using a software system, I've seen a lot of systems that have failed because of that. You really have to take the discharge flow measurement from the compressor room and correlate that with the amps to get a true kilowatt per 100 CFM specific power. Inspection and testing of air treatment equipment. Is the air treatment equipment functioning properly? It's not so much related to energy savings, but it is related to process improvement. If a customer has air quality issues in the facility, there could be undersized equipment. They bought a cheaper dryer. That dryer now is imposing a 10-pound pressure drop on the system, which correlates to 5% energy deficiency. These things all have to be looked at before and after the air treatment and how they're using the air treatment. Analysis of the piping system. We have AutoCAD people that can update drawings for customers. A lot of clients we walk into don't even have drawings for the compressed air system. You really have to look at the size, diameter of the pipe, how much air is going through it. Is there velocity issues with the piping? So you want to take an analysis of your data, which you should accumulate flow, pressure, amperage, kilowatt readings, and really determine what's going on in relation to the system event. There could be a dust collector going off, which we see on the flow meter as a spike. That's causing a third compressor to load up. These are all things that you need to really look at over the period of measurement of a week or 2 weeks where you're recording every second. Essentially, you should have a good understanding of what's going on with the system. And lastly, assistance with the implementation of an energy plan. Obviously, anything that you do at the outset of an audit, you want to see long-term sustainable savings. So you should have an energy plan in place at the outset that you're going to assist your customer with implementing and retaining those savings. Leak detection, again, it's very difficult for a lot of our clients to stay on top of. A lot of older plants especially are a lot of threaded pipe, and it's something they continuously have to stay on top of. It's the 80-20 rule. I tell a lot of my customers 80% of the larger leaks, or 80% of the loss comes from 20% of the largest leaks. And without even investing in ultrasonic equipment, I tell my clients, if you're down on a Sunday or you have a shutdown in the plant, have your millwrights or have your maintenance guys walk through the plant, and even if you tag and fix the audible leaks, that's going to be 80% of the loss without having to get into doing ultrasonic. If you can afford it and you can maintain a leak management program every 6 months or once a year to invest a couple $1,000s in a leak detector and some tags and train your guys, or have a consultant like ourselves come in and train your guys on how to do it every 6 months, the payback is pretty quick. If you look at the average is 20% of loss. On a 1,000 CFM system, that's 200 CFM or 50 horsepower worth of savings. So it's worth it actually to do this exercise once a year, even if you're just walking the plant and fixing audible leaks. So the other advantage of having a flow meter installed is that we can actually, if we have customers that run 24/5 or 24/6 and you've got a down day or you've got a period of non-production on a holiday or something like that, you can actually catch the quantity of flow going out towards, I'll call it non-production period in the plant, but going out to leak losses. Now, this is a little bit off because when you're not running any production, the pressure basically raises in the plant because there is no demand, essentially. So I always tell customers we kind of go out and measure leaks or tag leaks and quantify the leak based on the dB rating at the point of use, and we correlate that with the flow measurement. So usually we're within 15–20% because you're going to get a larger flow out of those leaks once the pressure profile raises because there is no production. When you're in drawdown, basically you're going to have a lot less leakage because the compressed air is being consumed and the pressure is lower in the header. System pressure drop. Pressure drop, again, causes false demand on the compressor systems by forcing the system to run at a higher necessary pressure to overcome line losses. For every 2%, as we mentioned earlier, it's 1% to overcome this loss. Small diameter pipes in the distribution system we've seen can sometimes cause an additional 20% energy because a lot of customers, in order to avoid having to deal with TSSA, where anything over 3/4 inch you have to have TSSA certified contractor and TSSA come in and certify the piping. So we see a lot of small diameter pipes that customers will put in to drop to a new machine. That new machine needs 120 CFM at 100 PSI. So they're throwing a 3/4 inch or a 1/2 inch line to that machine. Now they have to run that machine at 120 PSI in order to get that flow through the restriction that's caused by the lower diameter pipe. The other thing we see is in the compressor room generally is the biggest problem because if they've added a compressor, they've added 2 compressors over the years, and they put in a 2-inch piping system and never bothered to upgrade the main compressor room header, the trunk, so to speak. That usually causes a lot of pressure differential before the air even gets out to the plant, whether they have a loop piping system or not. Power logging, load profiles should be performed on each compressor, showing the true performance of each unit in kilowatt per CFM or kilowatt per 100 CFM, which is the specific power. Multiple compressors can be logged simultaneously to give a truer power consumption of the air system. In order to get true kilowatt consumption, you really have to look at the power factor. It has to be measured on each compressor, and you have to account for that in the amps and voltage measurements to get a true kilowatt. Flow measurement, again, flow measurement, we use, I've gone through several different types of flow meters over 15 years and found thermal mass to be the most accurate when it comes to dealing with compressed air. It's basically inserted directly into the distribution header. We can either do a hot tap or we drill a saddle, a Victaulic type saddle into the header. There's no access downstream of air treatment equipment. But in order to really, we can actually recalibrate this meter for different line sizes, so we can actually take the meters into other areas of the plant and measure specific processes if we're looking at energy savings by shutting off processes or relegating specific compressors to a process. You need to know what the flow is and pressure at that process. You can't really accurately assess the efficiency of a compressed air system in kilowatt per 100 CFM without determining what the true power and what the true flow is going into the facility. The other thing we can measure with the flow, obviously customers that we audit will have fluctuating demands throughout different shifts. This gives you an example where we can look at the average flow throughout a day shift. We can look at the peak flows. What are those peak flows? Are they short periods of velocity surge, or are they sustained flows? What is causing those in production, and can we somehow balance those out or take those out with either storage or changing somehow that process? This is like an afternoon shift where you've got a bit more average steady demand without the peaks, and then a night shift. Again, you can have 3 very different dynamics over 3 different shifts. So you really have to look at the peaks and averages of each shift, and then the peak and averages of each day, 24 hours, and then a week. Inspection of the compressed air system, really you have to look at every aspect of the air system, the compressors, the coolers, the dryers, the filtration, drains, how the compressors are being controlled, distribution piping, point of use practices, how they're using compressed air, all needs to be documented, and if there's any opportunity for changing any of those aspects in the compressed air system, those recommendations for changes have to be shown alternatives. Should we use a blower instead of compressed air? Should we use electricity instead of compressed air? You really have to provide an alternative. You can't just assess something as an energy consumer without providing a cost-efficient alternative. And not every instance is it feasible to replace compressed air with a blower or to replace compressed air with another type of energy source, because that would mean running electricity to that spot. It would mean running additional piping. You would have to, you really have to look at the cost of energy versus the cost of an alternative as being a viable or a non-viable change. As the other option, if you can't change that energy source, you can improve that energy source by adding air nozzles or some other, reducing the pressure at the point of use from 100 down to 50 psi if 100 is not required. In the study, you should have digital pictures which should show you what those problem areas are. And some plants that we go in and audit, aerospace, pharmaceutical, et cetera, don't necessarily allow pictures to be taken or will allow pictures to be taken with permission. But it obviously adds a bit of substance to the report if a customer can see the problem area that you're talking about and what the potential resolution is. Again, analysis and reports. You know, a lot of reports that we see out there are manufacturer-driven. The company has, you know, is a distributor for X ABC company, and they have their own manufacturers-driven software that they'll input data into, send it to the manufacturer, and then they send a report back outlining what should be done, which generally means purchasing their equipment. You really, from a report standpoint, there should be a comprehensive report outlining what the current operating system costs are, what the deficiencies are in the system, how to correct those deficiencies, and basically how to safeguard against potential system failures. Because it's not just about energy for the clients that we audit, it's about process as well, how to improve their processes by, you know, fixing dryer issues or fixing piping issues. Those are sort of collateral benefits to a proper compressed air system audit. Assistance should be available to your staff as well in implementing these compressed air management initiatives, going in and partnering with the company once the audit is done to say, okay, well, these are the problems that we have. How do we resolve these problems and provide these long-term solutions, such as setting up an energy management plan, setting up a leak detection, continual ongoing leak detection study once a year, et cetera. And how do we stable the system pressure? Can we reduce the pressure to 100 psi or 80 psi? Obviously, we have to work to integrate these measures into your process so that we don't interrupt the process as we're saving energy. So Module 2, we're going to look at pressure and unregulated users, velocity, and piping in compressed air systems. So looking at system pressure, whenever I walk into a facility, the first question I ask is, you know, are you having any problems with pressure in the plant? And generally, we get 4 categorical answers. You know, there is piping issues, there's restrictions, valve orifices, undersized piping, bottlenecks in the system, or we hear that there is no issue with pressure, and we go in and we find out the system is overpressurized. So they're running at 120 psi, because then nobody complains when we run at 120 psi, but instead of running at 100 psi, we're talking about a 10% extra energy in order to make sure nobody complains, because there was one event that happened and everybody dialed the pressure up because that one event was caused by a maintenance guy opening up a 2-inch pipe and blowing it across the floor. That's an extreme example, but those are the type of examples that we've seen in people overpressurizing systems. Undercapacitated systems, some customers have gotten to the point where, you know, again, you know, the production has brought in a new piece of equipment, an airline was hooked up to it. Maintenance doesn't necessarily even know that it's been installed, or they know it's there, but no idea how much air it was actually going to consume. So you end up with a, you know, a 50 horsepower compressor that's now running in drawdown because the system's overcapacitated. So you're having pressure problems because when they run that machine or one of the two machines, it draws the system pressure down to a point of critical failure. And the fourth being multiple compressor control schemes fighting each other for control of system pressure. You have a compressor loading up because there's a demand at the other end of the plant. That compressor then unloads and the pressure drops again, so we see pressure swings of 15 to 20 psi in the facility because the compressors are now fighting each other for control and loading and unloading because there's no correlation with what's going on in the facility itself as far as production is concerned. And again, when we ask, is there problems, sometimes there's low pressure all the time. Or this machine gives us a problem when the sandblaster operates, or our shot peen goes off, or we have no problems with overpressurizing. The most critical thing with pressure in the plant, obviously, is what is the lowest pressure that you can operate on and still have the plant function without any issue. And there's always a threshold there that we look at. If it's within 5 or 10 psi, you know, we try to tell our customers to bring the plant pressure down, you know, 1 psi a week or, you know, 2 psi a week, depending on how high it is, and just let the system stabilize, make sure nobody complains, and then, you know, a lot of times we've had customers that have got down to 85 or 90 psi and had nobody complain. But if someone knows that you're dialing the pressure down out in the facility, the first thing they're going to point to if there is a problem is the fact that you've dialed the pressure down, so dial the pressure back up. So it really has to be something that everybody buys into as far as lowering the plant pressure so that you're actually monitoring the process to make sure there's no issue with the process while you're dialing the pressure down. Highest pressure requirement can be the lowest volume ratio, again, required by the application. So there could be a machine in the plant that needs 120 psi, but it only needs 20 cubic feet a minute of air. So if you're running the whole plant pressure at 120 to satisfy one machine that only needs 20 cubic feet a minute, and using, basically by dialing the plant pressure up, all your leaks and all your unregulated users are now using an extra 200 CFM, that doesn't make a lot of sense, but we see it happening a lot. So in those cases, we've actually gone in and installed pressure boosters on that one application. We actually go in and measure the flow of that process and say, okay, well, you only need 20 CFM for this process at 120. So let's dial the plant pressure down to 100, and we'll put that 20 CFM booster now that's going to use 32 CFM because of its displacement to get to the higher pressure, but your 32 CFM that you're going to consume now is still much better than the 220 CFM in false demand that you create by running the whole plant pressure at 120. So that's really critical, is that we want to get down to the lowest plant pressure that we can operate on without affecting the process. And if there is 1 or 2 users where we can put boosters that are low volume users, and in some cases if there's a higher volume user such as a shot peen or a sandblaster that's affecting the whole plant operation, we can sometimes dedicate a compressor to that process. So when it does come on, which is infrequently, the compressor comes on and responds to the demand without impacting the plant, and the compressor shuts down when the process is ended, thereby not using any more energy. So it really depends on the situation and the process that we're looking at as to what we can get away with. Again, this is looking at a pressure band in the compressor cascade system where there is no sequencer, there is no integrated controls between the machines. On an unload-load basis, you really have to cascade an operation, for example, here between 3 compressors to a point where you've got those compressors that are working within a pressure band. So, you know, the unit number 1 is going to unload at 125 psi, load at 115. Unit 2 is going to come on, unload at 120 psi, load at 110. And your third unit in the circuit is going to unload at 115 and load at 105 psi. So really, you're operating within a 20-pound pressure band there in order to have the compressors come on and off, hopefully within a period of time where they're not going to stay loaded that long before they actually unload and shut down. So it's not necessarily the most efficient way to run. You want to, again, you got to drop 14 psi before number 3 loads, so you could have a vent going off in the plant, which is basically, before that third compressor comes on, you've now lost 14, 15 psi in pressure and could end up impeding operation of process in the plant. So you almost have to set your target that much higher to get that bottom load pressure to have that third machine come on. The other thing we have to deal with is you have multiple compressors and multiple dryers in a compressor room. your pressure signal for every compressor, it doesn't matter the control scheme, whether it's load, no load, variable speed drive, variable displacement, reciprocating, you've got a transducer which is integral to the compressor at the discharge of that machine, or a pressure signal which tells that machine what to do, whether to load, whether to back off on the variable speed drive motor, or whether to change the displacement of the rotor on a variable displacement. So what you're not taking into consideration is that you've got a dryer and you've got filters in the compressed air system that are now dealing with pressure differential across those filters. So your pre-filter and after filter on the one dryer could be running at a 5 or 6 pound differential. Your pre-filter and after filter on the other dryer could be running at a 10 to 12 pound differential. So now what you've got is you've got compressors that are designed to put out 101 or 102 psi that now have to run at a higher pressure in order to overcome that pressure loss through the air treatment equipment. So we don't really have a common pressure signal downstream that's actually loading and unloading the compressors. You've got individual compressor controls that are trying to fight across restrictions in the piping or the cleanup treatment equipment in order to satiate that demand out in the plant. When you've got multiple compressors set in a cascade type system like we just talked about, then you actually end up having to set your pressure bands at a much larger range in order to get your 95 or 100 out of the discharge of the compressor. You'll find a compressor, if it's running at 80-90% capacity, it's now got to run at full capacity to overcome that pressure loss just to get that 95 or 100 out of the discharge of the air treatment. I'm going to talk for a minute about unregulated users. Unregulated users are the worst consumers of air in the system. And leaks could be considered an unregulated user, obviously, because everything is a function of applied pressure in the compressed air system. But I'm talking about, using compressed air nozzles to blow on molds, or using compressed air to blow coolant off, using compressed air to dry parts, using compressed air to, even blow off production areas. Anywhere you're using compressed air in an open consumption fashion, and you're not regulating that compressed air pressure, you're using it at full line pressure. So if you have a 1,000 CFM system at 100 psi, and you've got 10 users that are open orifices that are using compressed air at 100 psi in a 1/4 inch line, you're going to consume 80-90 CFM on those unregulated users. If you can regulate, even without getting into engineered nozzles, if you can regulate that application down, or those air guns or those air nozzles down to 50 psi, it would probably do just as good a job at 50 psi as it does at 100, but the impact on the system obviously is greatly diminished because everything's a function of applied pressure. So when we go in and we audit compressed air systems and we look at the pressure in the distribution system, we measure the flow. A lot of times we're going to see the flow going up and down, and then we're going to see the pressure in the compressed air header swinging up and down. In some cases, we see swings of 25 to 30 psi. And what happens at the top end of the swing, if you're getting up to your 100 psi, then all those leaks and all those unregulated users are going to consume at that orifice chart rate at 100 psi, that larger volume of air. And when the compressed air header swings down to 80 psi, obviously you're going to consume less at 80 psi. But it becomes a vicious cycle, because in the mix of all that, you're trying to feed processes that have a dedicated consumption use to run your process equipment. So obviously, wherever you can regulate compressed air, usually we recommend, if you can do it at the source, fantastic. If you can lower the overall plant pressure down to 80 or 90 psi, that's great. Because what happens is when you have a process that has a regulator on it, and you think you're regulating that down to 60 psi from 100, well, we've actually seen systems that are swinging from 80 to 100. So now your CV changes across that regulator to some degree, where you're not getting 100 at the inlet anymore, you're getting 80. So you're actually changing and we've actually measured this, where you're changing the discharge side of that regulator, and sometimes where it's interrupted the process because the process is not getting a steady pressure. So again, the greater the compressed air pressure, the greater the consumption. Replacing compressed air, and this is where we get into looking at unregulated users and how you're using compressed air at the point of use, because I've gone in a lot of plants where it is not practical to replace compressed air. And although it seems to be a waste and whatnot, you're talking about running dedicated lines, putting in blowers where there's no power, running blower lines and air knives to places where it's really not feasible to fit it into the process. You really have to look at each process by process and find out if it is feasible or if it's not feasible. We've done a lot of situations where we've replaced compressed air with centrifugal blowers and air knives for drying parts, for blowing off process areas, food production, drying, etc. Generally, from a process standpoint, it's better than compressed air because generally these are oil-free blowers. They offer a heat rise, which aids in the drying process as well. And you can get, smaller engineered nozzles and air knives for blower systems that operate with much lower pressure. You're talking 3.5 psi or 100 inches of water column versus 100 psi. But it's the velocity in a lot of these cases which actually does the drying, the impingement velocity on the product or on the surface, as opposed to just smashing it with compressed air. So where it's not practical to look at blowers versus compressed air or change the process somehow, we do look at engineered nozzles, where if you can take that 1/4 inch or 3/8 copper or aluminum tube that you're using for blowing off your product or your process, and you put an engineered nozzle on it, you're actually increasing the velocity with the engineered nozzle, and you can get away with a much lower pressure and a lower consumption of compressed air by hitting it with a higher velocity at a lower pressure, as opposed to just hitting it with 100 psi through an open orifice. So at least when we're getting that regulated pressure down and we're getting an engineered nozzle in there, we have the same drying capability or the same impingement capability, but we're doing it with a lot less energy. In some cases, these nozzles can reduce compressed air consumption by 50%. Again, another good energy conservation practice would be to have solenoid valves installed to isolate compressed air flow during periods of no production. I can't tell you how many times I walked into process facilities and I found production machinery not running and compressed air is just hissing away through broken tubes or solenoids or valve gaskets that have gone. It would be a simple thing just on that 1-inch drop to that process machine to have a Ross valve or have a pneumatic valve that the operator can just punch that and shut off the compressed air to that process. If it only runs 8 hours a day or even runs 2 shifts a day, the off-shift savings would be substantial to pay for that valve at least by shutting off that process and not having to go in and repair those leaks. There's also customers we've gone into where there's complete areas of the plant that are down on the weekends, and if you have dedicated piping to those areas that ties into a loop at the back end of the plant, you've got a main 3-inch feed or something, just putting a simple solenoid valve in there or a butterfly to isolate that section of piping. Again, if it's 2 days a week or 2 shifts a week, still offers substantial savings enough to pay for that installation of that valve to not have any air going to that process and eliminating that leakage, at least for the period of time when there's no production. Unregulated uses, again, timer drains and there's been zero loss drains have been out so long now, it's almost funny when you walk into a compressor room and you see these timer drains, because there's been so much information on zero loss drains available to the customers out there. Really, when you look at putting a drain on a filter or a receiver tank or a dryer or a compressor after cooler discharge, the idea is that the timer comes on every so often for a certain duration, but every time that opens up, you're not only getting rid of the condensate, but you're expelling compressed air. The way a zero loss drain works is it works like a sump pump. You've got a limit switch inside of the drain, as you can see on the picture. So when the condensate and oil builds up inside the drain, it raises that limit switch and hits and actuates the solenoid. So when the solenoid opens to discharge the compressor condensate, it basically drains the sump down to the low-level switch and shuts the solenoid off before you actually lose any compressed air. And the idea of these drains are, they're $200–300 for a zero-loss drain. If you look at the cost over the course of the year, the paybacks are generally under a year from replacing these with the zero-loss drains. The other thing you're doing as a collateral benefit is if you have oil-water separators in your compressor room that are collecting oil out of the condensate in dryers and filters and compressors, by not pushing 100 psi condensate out every time, you're reducing the emulsification of the oil and allowing it a better separation efficiency on the compressor condensate separator as well. Compressor air velocity through the compressor system is one of the most overlooked components of audits, but generally one of the most important. We try to measure compressor air velocity when we go into the system. Obviously, pipes that haven't changed in 5 or 10 years that are now 2-inch that should be 4-inch is one of the biggest things we see out there in distribution systems. And basically, if you have a lot more air now or trying to push a lot more volume through an undersized piping system, it becomes very much like putting your finger on the garden hose. So in order to get the air that you need out there, it has to come out at a higher velocity in order to get through the piping system. So these tables are based on an ISO 4414 standard, which also follows BS 4575. Recommended flow rates through main piping headers. And most plants that we go into, when we look at the type of flows that they're putting out there, it's generally a lot higher than what we see on these charts. Ideally, if you can maintain a line velocity of 20 feet per second on main headers and 50 feet per second on branch headers, that's what's recommended. We see velocities upwards of between 100 and 200 on some branch lines, and higher than that on main lines, and higher than that on branch lines. So the idea of designing new systems or looking at re-engineering compressed air systems, it really has to be taken into account. How much air are you going to use now, and what are your plans for the future? So let's spend that extra couple $1,000s on a larger diameter pipe now, instead of just looking at a cost savings and we'll worry about it later. Generally, the worry about it later adds to a lot higher costs in operating down the road. So high velocity in air systems usually is an indication of basically 4 things that we look at. Inefficiently sized compressed air piping, which is the largest thing we see. Restrictions in the compressed air filtration or drying systems. I was in a plant last week where they hadn't changed the coalescing filters. They were completely pinned in the red, and the compressor had to run at an extra 20 psi just to overcome the line loss. When I opened the bypass on the filtration, literally the pressure in the compressor dropped 20 pounds. So it is a real thing, having the restriction in the compressors and dryers. Large capacity demands, which exceed the system capacitance for a brief period of time, such as the shot peen or sandblasting, dust collectors, things that use a large volume very, very quickly, where they're pulling a higher velocity through the whole piping system. And insufficient capacity of compressed air supply to meet system demands, where you just don't have enough compressed air capacity, so the velocity is high because it's pulling out basically all that you have available. How that relates to air quality is that you're pulling a higher than necessary velocity through air treatment equipment, through filters, through separators and compressors, through dryers, which are designed with their heat exchangers, et cetera, for a certain contact velocity in order to remove oil and moisture out of the system. If you're increasing that contact velocity, you don't have the heat exchange properties, and we've gone into plants which have huge air and oil problems, and the customer has no idea because they have dryers and filters why they have issues. And a lot of times we see it's because of high velocity is being pulled through the dryers and filters, which decreases the contact time and efficiency of the equipment. So by changing piping or adding storage or balancing the flow across the air treatment equipment, we can generally resolve those issues instead of just putting in new dryers. Piping issues, systems we walk into are designed one of 2 ways. They're either ring main, where they're looped in the plant, or they're a spur system where the piping is dead-ended. Spur systems will work, providing that they're sized properly and they have sufficient storage out there to deal with the events in the plant. Obviously, the most efficient being a ring main system where energy can be distributed from both sides. It's going around whatever way the demand is. It doesn't really matter because it goes both directions. As far as mainline and branch line connections, it's always recommended you take compressed air drops off the top of the header. These are just good engineering practices where if there is a dryer failure, you have moisture issues in the plant, water then has to work its way up from the main distribution line to come down to your process equipment. We recommend installing drip legs on process lines that you can drain out if there is a dryer failure. At least you've got the capacity to deal with it. Again, we walk into a lot of plants where we see point-of-use receivers installed. There's a lot of hoses installed. Generally, that's an indication that they're trying to deal with pressure issues out in the plant that were not resolved throughout the distribution system. The problem with that is when you add all these point-of-use receivers and then you feed them with small diameter hose, it increases the problem of the situation because these receivers now become consumers or demand initiators in the system because they have to be replenished once they feed the process. So it's better off to look at why this system is having issues with pressure instead of just trying to continually throw Band-Aids at it because it doesn't resolve the long-term issue. Just going to go through briefly before we finish up here, storage, control, and sequencers. production, treatment system, and optimization controls. In a well-designed system, you're generally going to see the compressors, air treatment, receiver storage, where it's feasible or plausible, a flow control valve to regulate pressure into the plant, and then a compressor network control to basically load and unload the compressors in a fashion off of one common transducer signal, which is generally in dry storage. That way you're trying to actually match the supply to the actual demand, providing you resolve the issues out in the plant as far as demand issues are concerned. So tank sizing and capacitance, what are you putting in a receiver tank for? I have customers that say I'm putting in a receiver so that I have storage. Well, just putting in a receiver doesn't necessarily mean that you have storage in the building. It means that if you have the same pressure in, it's the same pressure out. Basically, there's no storage going on. You've basically got a bulge in the pipe. So it will allow compressor controls to slow down and respond a little bit, but generally when you have a rapidly moving system that's using all the flow you're giving it, pressure in, pressure out, it's just going right through the receiver tank. And useful storage is the amount of stored air you can use to cover a system event expressed in cubic feet. If you have a specific event that's going off and you can apply storage to it, so we know exactly how many cubic feet per PSI we need, let's say a 500-gallon tank with a 10 PSI useful pressure, we'd be looking at 46 cubic feet to deal with that specific capacitance for useful storage. Obviously, you can't size a compressor storage tank to deal with having a compressor off. You'd be talking about a huge tank when you get into over 100 horsepower. So what we look at is well, this is why we really need to measure flow as well as we're measuring power, because we're going to see certain events that are going off in the process where we can actually remove that event by applying storage. And this is where we look at, for an example here, if we have a 400 CFM event with a useful differential of 4 PSI, we know that if we put a 500-gallon tank in, we've got 2.8 seconds. A 1,000-gallon tank, we've got 5.5 seconds. 1,500, 11.1, or sorry, 2,000 would be 11.1. So really, when we look into measuring the flow, we can actually isolate that demand out of the system and say, okay, well, this is happening. We have a 400 CF event that's happening for 10 seconds. We know that if we put a 200,000-gallon tank in there, we've got our differential of 4 PSI that we can deal with that event and remove it from the compressed air system without having to load a fourth or a third compressor. This is where we make a difference on the demand side savings, where we can say we can deal with storage, take that event out of the circuit, and stop that compressor from loading. Because once it loads, you've paid the demand charges, even if it unloads after a brief period of time when the event is satisfied. Flow control valves, there's been a lot of talk about flow control valves over the years, whether they're good, whether they're bad, whether you need one, whether you don't need one because you can use a VFD. When we look at large distribution systems that have a myriad of piping, and I'm talking about plants that are 300,000, 400,000, 500,000 square feet, and you've got a huge myriad of piping out there, and the compressor room is centralized at one end of the building. You have a transducer on each compressor that is designed to control what's going on in the piping system. That's at the other end of the plant. That transducer is back at the compressor, so it doesn't necessarily know what's happening at the far end of the plant. It doesn't know that your shot peen's gone off. It doesn't know that your blow-offs are working out in the plant. All it knows is it needs to maintain a certain pressure back in the compressor room based on its set pressure. One advantage of the flow control valve, and again, without storage, a flow control valve doesn't work. You need to have the storage behind it. The principle there is that you should have enough storage behind the flow control valve that you're able to take things like those events that I talked about in the last slide out of the distribution circuit by applying storage to it. What the flow control valve is, it limits the velocity of compressed air through the entire piping system by maintaining a steady pressure. Because with the pressure swings that we see in compressed air systems without proper storage of 20 or 30 PSI, we've got this swing going on where we've got 15, 20, 30 pounds of swing out in the pressure in the system, and which is causing operating problems with process, because that process may not be able to work at 80 PSI, and at the bottom end of the swing, it's just happened to catch that part of the production that needs 100 that's now got 80. A flow control valve's purpose is to maintain a steady velocity and pressure throughout the piping system and allow you to deal with certain events out of storage or stabilize the system pressure by applying enough storage in it, similar to a lake in a dam or a capacitor and a resistor. If you just put a flow control valve because someone happens to sell it and they have access to it, where we've seen these things bypass because they don't work is because there wasn't sufficient storage or there wasn't enough differential on storage in order to maintain proper downstream pressure, and they just get bypassed and say they don't work. They do work in the right application. Again, the idea is with fluctuations in the swings of the header, but you got to have usable differential and you've got to create that stored energy. If you can't, it's not worth putting it in. This will give you an example, this graph of flow controller installation. The high pressure side of the receiver tank, you can see on the black line where the receiver tank is now going up and down in pressure, but the discharge side of the receiver through the flow control valve is maintaining a steady 1 or 2 psi out into the distribution system. So the purpose of the valve is to open up and allow volume out that you need, but doing it at a steady state pressure within a couple of pounds. That's what limits the velocity through the system, but allows the flow out that's needed for production. Again, a lot of manufacturers say you don't need a flow controller if you have a VFD, because the VFD will trim the plant up and down, similar to a modulation valve on the flow controller. But what KGI says, that is basically what I'm saying. Every application is different. There are clearly systems that would benefit from the stable, constant pressure that a flow controller can provide in a very dynamic system, and part of that load efficiency of a VFD compressor. Even with a flow controller and proper storage, an optimized system will fill the storage in the most efficient manner. In many systems, it can include a VFD compressor. So segregating supply from demand, to me, is very important, because really you're allowing the compressors a time to deal with events in the plant through storage and control, including VFD, because really the VFD will trim at the bottom end to make sure receiver tank has enough volume when the flow controller is opening to maintain that volume out in the system at a steady pressure. Providing there is sufficient storage, it'll work properly. Where I've seen VFDs fighting flow controllers is when there's insufficient storage or insufficient differential across storages to deal with those events out in the plant. Or there's such a large event in the plant that it really, there's too much volume that would have to be applied in storage to deal with that event, and this is where you have to look really on the process side to see what's happening out there. Are we better off dedicating a compressor to that process or dealing with storage out in the process side to deal with that specific event? Compressor controls, I'm going to go through quickly. Few air systems operating full load all the time. Part load is where we see the biggest savings, and these are obviously influenced by the type of compressor controls. You get into multiple compressor systems, it becomes very complex because you've got different control schemes that are fighting each other for control of what's going on out in the plant. First type of controls, without getting into reciprocating compressors at the smaller end, you've got low node compressor controls. These are basically, you have to operate within a pressure band like we talked about, where basically the compressor unloads at 110, loads at 100, so it operates within that band. So the motor and the air end rotors turning at a constant speed. The air inlet opens to the rotors, so the air is making 100% of its rated flow, and basically closes when it's met its rated flow and pressure. When it unloads, motor and air end are still turning at constant speed, but the inlet valve is closed. The air end is still turning, but producing zero flow. So basically, you're only consuming 15 to 35% of full load power, but not producing any flow. We get into modulation compressor controls are generally the least efficient, because what happens is the inlet throttle valve basically opens and closes in order to maintain a steady pressure at the discharge of the compressor. So the initial benefit to this type of compressor control scheme was that you're going to maintain a steady pressure in the plant. But as energy efficiency grew and became more prevalent in applications of compressors, people started to look at that and say, well, okay, well, I'm maintaining a steady pressure, yeah, within 3 or 4 psi, but when I'm only using 20% of the compressor capacity, I'm still consuming, 80, 90% of my energy in order to do that. So the really low end of the modulation curve is not very efficient. Sorry, I'm just trying to. Sorry. Okay, variable displacement basically just changes the rotor length on the compressor, so it drops the amps on the motor. You're changing the compressor volume or the ratio using a sliding vane or a turn valve. Those are usually applied in conjunction with the modulating valves to provide more accurate pressure control, but you're getting part load efficiency. Last being variable speed drive compressors, where you're actually changing the compressor is changing its energy consumption on the motor by basically modulating the motor up and down to maintain a steady pressure. So these will maintain a steady pressure within a certain range, and the motor will ramp up and down in order to consume less energy. Where you get into problems is, again, you need to match your variable speed drive to the demand. You want to be in the sweet spot, 50 to 80%. When you start getting below that, you start to lose efficiency across the air filtration. You start to lose efficiency across the rotor. So it's not as efficient if it's not applied in the right application. So you really have to look at variable speed drive as not being the best solution to every application. It has to be applied as a trim machine or as a standalone machine within the right capacity range. I've seen customers put in large VFD compressors to deal with potential expansion and end up with air quality issues because the separator is not getting the velocity across the separator to affect proper oil removal. So they end up with oil carryover issues, or they end up with oil in the condensate because they're not getting enough heat generated for the compressor to burn the condensate out of the oil. So really have to look at a variable speed drive as not just a drop-in, we're going to solve all our energy problems. It has to be applied properly in the right situation, which is why you really have to monitor the system and take into account everything. Compressor controllers are, again, a great opportunity for energy savings because we're now taking the control away from individual transducers on each compressor, and we're taking it over to one central transducer in the storage tank, and then the master controller tells which compressor, whether it's inlet valve modulation, whether it's load, no load, or whether it's VFD, it's deciding which is the most efficient way to run to maintain a steady pressure. Key performance indicator, just to wrap up here, we want to look at is our ability to monitor and resolve what the specific power of a compressed air system is expressed in kilowatt per 100 CFM. This is the most efficient way to do an audit in a system and to get that information out of the system with accurate monitoring to say how many kilowatts per 100 CFM am I using. Because that specific power is really what's going to drive any future sustainable savings in a plant. How do we reduce our specific power? How do we reduce our kilowatts per 100 CFM? Because then it doesn't matter what your production is. It doesn't matter whether you have summertime busy, wintertime slow. It doesn't matter if you add another 10 machines to the plant. If you're doing it at the lowest specific power, the lowest kilowatt per 100 CFM, it's going to be the biggest bang for the buck. I think that wraps it up.
All right, perfect. Thank you, Chris, for joining us this afternoon, and a great overview on how businesses can access support for compressed air systems. So we have some time for questions, although we are at 2 p.m. right now. So if you'd like to stick around for questions, we do invite you to do so, and you can type your questions into the chat bar. For those who are leaving, thank you so much for attending our webinar. On behalf of Enersource, Hydro One, and Partners in Project Green, thanks for joining us this afternoon. And if you want to find out more information, feel free to visit our websites or contact me at acerbu@trca.on.ca for more information. So our first question is, how do you relate compressor efficiency with production level?
You really have to look at, we've just gone through this in a couple of plants where we have to look at what their process is doing. And in larger facilities that we deal with, they actually have people that are monitoring what their process is doing, how many machines are running on a specific day or a week or a month. And we can actually look at how they're using compressed air during that monitoring period. I'm talking about doing a preliminary engineering study where we're actually in there monitoring for a month or 2 months. And in one cases with this particular client who had fluctuating production throughout the course of the year, we actually monitored for a 6-month period. We were actually able to look at, with their production people, how their production related to how much compressed air they were using and what energy they were using to produce that compressed air over that period.
Okay, perfect. So it doesn't look like we have any more questions at the moment. But once again, if you think of anything, feel free to email me, and I will get you in touch with Chris right away. So once again, thank you for staying on the line with us and attending this webinar, and have a great afternoon. Thanks. Bye.
Thank you.